Okay, so now let's take a look at this nonlinear system of two first-order differential equations that we just derived for the pendulum. So theta is representing the position of the pendulum at time t, and v is representing the velocity of that pendulum at time t. So the first question is, well, how many equilibrium solutions does this system have? And based on the context, without doing the math, let's think about whether those equilibrium, whether we expect them to be stable or unstable. Okay, so to find an equilibrium, what we would want to do, we're not going to change what an equilibrium is, and we've already considered equilibrium of nonlinear systems, is we would want to solve simultaneously what happens when we set both of these derivatives equal to 0. And so we can see from this equation over here, very trivially, that first of all, the velocity needs to equal 0. And so if you think about that, if the pendulum has any velocity which is non-zero, its position is going to change as time goes on. So certainly it wouldn't be considered an equilibrium condition. So one thing right away is we need the velocity to be 0 in order to guarantee that the pendulum is not going to move. That hopefully makes some intuitive sense. And so now if we plug that condition in to the second equation now becomes minus the sine of theta is equal to 0. And so when is the sine of theta equal to 0? Well, that's going to be for any value of theta, which is a multiple of pi. Okay, so here k is denoting an integer. So that means we have an infinite number of equilibrium. Okay, and in fact, any point theta v where theta is equal to some integer times pi and v is equal to 0, all of those points are going to be equilibrium solutions. And if we kind of think about these cases, well, if k is equal to 0, plus or minus 2, plus or minus 4, so on, that means at time 0, its initial position would be located over here, and these are going to be stable equilibrium. You would expect as time goes on, even if we start a little bit off from that position, it's going to settle back down into its equilibrium position. So we might think that these are going to be stable, and that's a pretty good idea there. On the other hand, if k is equal to an odd number like plus or minus 1 or plus or minus 3, so on, that means it's located up here at the top at time 0. And now if you think about it, if you position this pendulum just a little bit off from its equilibrium, if it were over here, as time goes on, it's not going to settle back down to its vertical position. It's going to move and it's going to settle back down over here to at the other equilibrium. So if k is an odd value, then we might expect that those equilibriums are going to be unstable. Okay, so here we're kind of just doing this analysis based on some of our intuition, and we'll show all of these things. We'll prove that all of these things are true mathematically, but I just want to make sure that we're able to attach some meaning to the behavior of these solutions. Okay, and now in part B, it is telling us that we can approximate the term in the equation for dv dt that had the sine of theta with a linear function. And so let's see how that goes. I ran out of room over here, so let me create a new slide and we'll do the work for part B on that new slide.